were working on so many things. So last class I was explaining to you about permanent magnets, and we were just discussing about how the magnetic field of a permanent magnet, how the magnetic field for a permanent magnet is. So that was one topic that we discussed. After that, we also discussed about magnetic moment, and I was just explaining to you that when you take a bar magnet and then place it in an external magnetic field, it orients itself in the direction of the external magnetic field, that is North Pole pointing towards the North Pole and so on. Yeah, so we continue from there. I hope you are able to hear my voice, and I also hope you are able to see my screen. So these are two things. If I can just get some hint from you. Yes, sir. Yes, sir. Yes, sir. So yes, so let us continue from there. I was held up with the works, that's why I was not able to come on time. That's why I asked the class for 3 o'clock. Okay, so let us continue from there and then let us work. So the next thing that I should be discussing about is more about magnets. So I had just told you last time that if there is a magnet here, and if this is the North Pole and if this is the South Pole, we assume that the entire polarity is at some point here. We assume the entire polarity is at some point here. This is just an assumption. Based on that, we define something called as the pole strength. Okay. Now I have not seen any question of this kind in the board exam, nor have I seen any question of this kind in the entrance exam. And also the other thing that I have to tell you is that lot of portions from this chapter has been removed. Okay, but I am a teacher, so I have to teach what is required for the student. Okay, so now let us do a few questions based on this pole strength and based on magnetic moment. Now suppose there is a bar magnet which has some magnetic moment m. Last class I asked you, suppose you split it into two this way. I asked you, if you just take this, what is the time period for simple oscillations. So I explained to you that torque is equal to I into alpha. This is equal to m cross b. So that is equal to mb sine theta. Then I explained to you, for small angle sine theta is equal to theta. So I can say I alpha is equal to mb theta. Now these kinds of questions have come in the entrance exams. I have not seen this in the board exam, but this has come in the entrance exam. So now alpha is equal to mb by I into theta. This torque is of a restoring nature. Restoring nature means if this is how the magnet is oriented, and if you turn it this way, it tends to come back to its mean position. So that means it's in stable equilibrium. If it's in stable equilibrium, this thing is equal to omega squared, and t is equal to 2 pi by omega. So t is equal to 2 pi root over of I by mb. Now when you split it into two halves, what happens is I becomes half because mass becomes half, L remains the same. Magnetic moment becomes half because polarity kind of becomes half. So half in the numerator, half in the denominator get cancelled, and there is no change in magnetic field. This is where we were last time, and I told you I'll explain more of this again in the next class. So we go to the next session now, and the next session we focus on this. Suppose I take the same magnet. Suppose I take the same magnet and cut it into two halves this way. Now what will happen to the time period? So time period is 2 pi root over of I by mb. So now what will happen? If you just take this much, suspend it in the middle by a thread, what is its magnetic field? What is its time period for simple oscillations? So the way you go ahead with it is this. Now moment of inertia is ml squared by 12. Now when you made it half, mass will become half, length also will become half. So moment of inertia will change 1 by 8 times. Yes. Now when you cut it this way, what will happen to m? The pole strength will remain the same, but the length will become half, so it is becoming half. So this will become 1 by 4, and when you do root over, so it will become half into 2 pi into time period. I mean 2 pi into root over of I by mb. That means it will become t by 2. That means it will start oscillating with a smaller time period. Can you make some notes here? Can you please try to understand this? I will be back in a second. Sir, is permanent magnet the portions for this week? Yeah. Yes, it is magnetism. It is magnetism. No, class won't change. Only today I requested for a change because otherwise I would have had to miss the class. That's why I said, Krishna, Sri Nilan, not every time. Today alone. Yeah. So if this is understood, then I will go to the next question. The next question that I have is, I take a magnet this way and I take a magnet this way, and now I suspend it, and now I turn it by a small angle and release it. Now what is the time period for oscillations? I take two magnets. I take two magnets. So this is the north pole, this is the south pole. This is the north pole, this is the south pole, and then it is oriented this way. Now what is the time period? What is the time period? What is the time period for simple oscillations? Okay, so now t is equal to 2 pi root over of I by mb. Now I, there are two, so axis is the same. Axis is not the same. You want to know what moment of inertia about? This is the axis about this. So axis is going to be the same. So it will be ml squared by 12 plus ml squared by 12. So that will become ml squared by 6. So moment of inertia is ml squared by 6. But this m now this magnetic moment is a vector quantity from the negative pole towards the positive pole. From the negative pole towards the positive pole. So you will see that it will have a root over. So it will become root 2m. Yeah. So instead of m here, you have root 2m. So t is equal to, so now you can work it out, 2 pi root over of I by 2, sorry, 2I by root 2 mb. So this goes up, and then again, so accordingly the time period increases. Time period increases means it goes slower. So I hope you are able to understand this particular concept. Won't the north pole of first magnet move towards the south pole of the second magnet? So doesn't that affect the answer? Oh, okay, we are assuming the external magnetic field is strong enough for there to be any interaction. So if axis is at the tip of the magnet, then ml squared by 3. No, axis is not at the tip. Axis is not at the tip. This is it. This is it. So now if I turn this like this, it goes back. So if it goes back, it is rotating about this axis. Now you have one magnet here, and you have somehow stuck it with another magnet here. So now both of them will rotate about this point only. So it is not about the tip of the magnet. Okay. So this is the previous slide. Here it is at the center. Okay. Yeah. So, so here you wanted to see the previous slide. Okay, so these kinds of questions sometimes they have come. I hope we are able to get it. See, regarding your board exam, don't worry about your board exam. Okay, I will give you a set of 30 questions or 40 questions. Out of those 40 questions, invariably 7-8 questions will come. Okay, and don't worry about your board exam. Worry about the entrance exam. Worry about understanding the subject. In your entrance exam in physics, if you score 8 to 10 questions correct, you get a 99 percentile. Okay, this speaks about the general national ability as far as physics is concerned. It is because people look for, I mean, people just don't try to understand. Basically, you know, everybody, your friends, you spend so much time with your friends to develop friendship. Same way with the subject also. Unless you spend adequate time, this subject cannot be learned. Okay, so understand that. Spend time with this. Don't worry about your board exam. Board exam, if you do what I am going to tell you to do, you will easily get 85, 90 plus in your board exam. But adum pandradilla, not many are doing it, but I'm just telling you, there's no point preparing for your board exam from now. Understand the subject. The same thing will be asked in your board exam also. Okay, so this is it. This is it. So these are questions related to the permanent magnet. Okay, so first thing I'll tell you is a lot of this is deleted portion. A lot of this chapter is deleted portion. So don't worry about it. Second thing I'll tell you is that this chapter is a little tricky. So make sure that you are focusing and understanding. So as of now, what is it that I have completed as far as this chapter on magnetism is concerned? Magnetism and magnetic properties of material. So first thing is how to compare a permanent magnet with the solenoid. So the comparison is via its magnetic moment. Okay, magnetic moment. Magnetic moment, basically there are two ways of defining it. Simply speaking, it is NIA for a solenoid. For a solenoid, it is NIA, and for a permanent magnet, it is pole strength into 2 times length. This is what is called its magnetic moment. Okay, so now this pole strength concept, they have removed it from your syllabus. You don't have pole strength concept. Even in your board exam, they have told clearly there will be no questions based on pole strength. Even before, they were never giving any question based on pole strength. So now, if you want to compare a solenoid with that, so pole strength into 2 times L, which is the magnetic moment, is equal to NIA. Okay, so now you can compare between the two. So the L comes down. This is current area by L. So that is ampere meter. So this is the unit of pole strength. That is the question that has come in your exam. Okay, then I am also further telling that this is a magnetic dipole. A magnetic dipole is exactly like an electric dipole. So this is the axial point of a magnetic dipole. Now electrostatic force, we said F is equal to 1 by 4 pi epsilon naught Q1 Q2 by R squared. Same way here, we will say the magnetic force is equal to mu naught by 4 pi pole strength 1 P1 P2 by R squared. Okay, so this is the magnetic force, this is the magnetic force, and this is the electrostatic force. So they go hand in hand. So the dipole moment at an axial point. So dipole moment at an axial point is equal to, the electric field at an axial point is equal to 1 by 4 pi epsilon naught minus P by R cubed. So exactly the same thing. So the magnetic field B at an axial point, sorry, at an equatorial point is minus 1 by 4 pi epsilon naught magnetic moment by r cube. They go hand in hand. For every quantity on this side, you have a quantity on the other side. Only thing is, I explained to you in the last class that there is nothing called as magnetic potential energy. Okay, but a bar magnet has potential energy because of the magnetic field, but we don't talk of magnetic potential. The reason is magnetic fields, we don't say whether they are, we don't ask the question whether a magnetic field is a conservative field or not, and that's what we saw in the last class. Okay, then electric field is equal to 1 by 4 pi epsilon naught 2p by r cube at a axial point. Exactly the same way here. B at the axial point is, hey, I wrote 1 by 4 pi epsilon naught. No. Mu naught by 4 pi. Mu naught by 4 pi. The constant here is mu naught by 4 pi. Mu naught by 4 pi 2m by r cube. This is the B at the axial point, equatorial point, equatorial point. So they go hand in hand. Everything goes hand in hand. So magnetic field and the electric field, they just go hand in hand. Every quantity here, you have a quantity there. Torque is equal to m cross B. Here here P cross E, here m cross B. Then work done is equal to P is cos theta. Here it is mb cos theta. So everything is the same. Okay, so if you understand this, then we can just move on, and then again the derivation, there is a derivation in your book. You will never be asked the derivation. Anyway, they have removed it from your syllabus, so you don't have to worry about it. That is, a bar magnet can behave like a solenoid, or a solenoid behaves like a bar magnet. So the derivation to show that the magnetic field due to a bar magnet at an axial point is equal to whatever we have seen. So there are some proofs in your book. Those proofs are not required. Okay, what is required for the NCERT board exam is only the Earth's magnetic field, The second thing is magnetic field due to a bar magnet, and then what happens when a magnet, what happens when a magnet is placed in an external magnetic field. Okay, so this is what is there mostly in your syllabus. In fact, even the difference between ferromagnetism, ferromagnets, diamagnets and paramagnets, they have removed from your syllabus. The difference between ferromagnets, paramagnetism and diamagnetism. This is where they used to ask questions for in the NCERT board exam, and that they have removed from the syllabus. Okay, so this is what is required for you. So slowly we will reach there. We will continue to read about all these things. Just let's spend time, and then it will work out. Okay, so next I explain to you about a bar magnet and how a bar magnet works. Now we need to visit little bit about magnetism. What is magnetism? What is it that causes magnetism? So in the last class I explained to you that, look, not the last class, the very first intro class, I explained to you that magnetism comes from the electron. This is the root cause of all magnetism. How the electron is interacting with the nucleus, or what is the magnetic moment due to an electron. So if this is a nucleus, and if an electron is rotating around it in the nth orbit, then I want to know, so I will give you a question. What is the magnetic moment associated with an electron in nth Bohr orbit. My neighbor basically is having COVID, and that guy is not taking care of himself. So there is a nurse who comes from the government side, and this is the time for her to come, and then she just comes and shouts. So that's the whole thing. Okay, so here is a question. What is the magnetic moment associated with an electron in the nth Bohr orbit? Try to do this question and I'll work it out. Okay, so if I have to answer this question, magnetic moment is basically I into A. What is I? Q into frequency into A. What is frequency? Frequency is 1 upon time period. What is time period? Time period is equal to 2 pi r by V. So it is Q into 2 pi r by V into, sorry, that is time period. So it is Q into V by 2 pi r into pi r squared. Pi gets cancelled, r gets cancelled. So the magnetic moment is equal to QVR. Okay, QVR is the magnetic moment. Now we know that MVR is equal to NH by 2 pi. So from there I can say VR is equal to NH by 2 pi M. So QVR by 2 will become equal to QNH by 4 pi M. And this is the magnetic moment associated with one electron. Magnetic moment associated with one electron. Okay, so this is a board question, very important board question, comes quite frequently. What is the magnetic moment associated with an electron? So now, as you look at species, helium has no unpaired electrons. So if something has no unpaired electrons, it is a diamagnetic substance. Okay, copper is another example of a diamagnetic substance. Then you have sodium, aluminium. These are all paramagnetic substances. Paramagnetic substances because they have unpaired electrons. Then you have certain materials like chromium, nickel, cobalt, iron, which have large number of unpaired electrons. Now these show a property called as ferromagnetism. So there are these three effects in a medium. One is diamagnetic substance, then there is a paramagnetic substance, and then there is ferromagnetism. But in every material, fundamentally, there are only two interactions, two ways in which the electrons can interact. One way, they induce magnetism. In the other way, they align in the direction of other electronic magnets. So it is the magnetic quantum number. Magnetic quantum number is what is giving rise to this. Now, when there is induced magnetism is always opposite. So 1 plus 1 will here become 0. Why? Because whatever has induced on the other one, they will be in the opposite direction. So the net magnetism will be 0. Now such materials, this property is what is known as diamagnetism. Those materials which show lot of diamagnetism are called a diamagnetic material. Okay, if at all you get questions from here, you may get in the entrance exam. In the board, they have removed this part. Okay, then if this property is more, such materials are called paramagnets or paramagnetic materials. Extreme case of paramagnetism gives rise to ferromagnetism. Okay, extreme case of paramagnetism gives rise to ferromagnetism. Okay, this is extreme magnetism. This is extreme cases of magnetism is ferromagnetism. Okay, before I just proceed, I just wanted to discuss one thing. See, I want you to understand Tesla. I want you to understand Weber per meter squared, and I want you to understand Weber 1B. Okay, Weber. So first, units of magnetic field. Magnetic field is Tesla. Okay, now Tesla B into area is flux. Unit of flux is Weber. Okay, so Weber per meter squared is equal to Tesla. Okay, so this is how this can be a unit of magnetic field. This can also be a unit of magnetic field. Okay, so now this can also be, yeah. So now you have solenoid. Magnetic field comes from a solenoid. So mu naught Ni. So you leave this mu naught. So this N into I. N into I, basically N into I into A. This will give you the N into I into A will give you the magnetic moment associated with the solenoid. So now magnetic moment divided by length will give you pole strength. So if I am finding out pole strength, there are two ways I can get pole strength. One, I can get from this ampere meter. Okay, this area is meter squared L, so I'll get ampere meter. So pole strength is equal to ampere meter. Now another way I can get pole strength is from this whole concept of magnetic moment or Tesla. So force is equal to Tesla into pole strength. So this Tesla into pole strength, 1 minute. Just 1 minute. Okay, so pole strength. I want to explain about pole strength. So I said force is equal to mu naught by 4 pi P1 P2 by R squared. This bipole strength is equal to Tesla. Okay, so Tesla, yeah. So do you see that Tesla is equal to, this is magnetic field B. Okay, so B has a pole strength here. Okay, so B is, so Tesla into pole strength, Tesla into pole strength is equal to just a minute. I basically want to relate pole strength to Weber. Okay, I want to relate pole strength to Weber. So if I multiply this with area, if I this is magnetic field, if I multiply this with area, This is Weber per meter squared. Then if I multiply it with area, I'll get Weber on this side. Okay. So I'm trying to see how basically this mu naught is creating some trouble for me. So, okay, just a minute. So Tesla is equal to Weber per meter squared. Weber per meter squared. That is equal to force divided by pole strength. That is equal to mu naught by 4 pi into pole strength by area. So this area gets cancelled. So Weber is related to the pole strength. But this mu naught by 4 pi, what to do with it? Okay, fine. Okay, I'll get back on this. Give me a little time and I'll get back on this. Yeah, so let us work with what we were doing. So I was telling you that there are two properties. One is diamagnetism and the other is paramagnetism. Then I told you extreme case of paramagnetism is ferromagnetism. So let me explain to you what happens in ferromagnetic materials. Basically, in ferromagnetic materials, suppose this is a ferromagnetic material, the influence of each other's of the large number of unpaired electrons gives rise to specific areas called domains. Okay, so here the atomic magnets are all oriented in one direction. Under the influence of each other, they are all in one direction. They are all in one direction, such that overall there is no magnetism. But there are specific regions. So these are called domains. So there are specific regions where the magnets are all oriented, the atomic magnets are all oriented in one direction. Okay, so such a material is called a ferromagnetic material. Okay, now in case of paramagnetic materials, there is an interaction which makes them oriented in the same direction, but there are no domains. So even here they will be oriented in different, such that the net magnetism at any point is zero. Net magnetism over small areas will be zero. In case of ferromagnetic material, there are large areas where there is some magnetism, but overall the magnetism is zero. In case of diamagnetism, there is no magnetism and they are all having zero magnetic field. Okay, now suppose this is a external magnetic field. Now this is an external magnetic field. If you keep a diamagnetic material here, the induced magnetism in the diamagnetic material will be opposite to it. As a result, it will tend to move away from the magnetic field. A diamagnetic material tends to move away from magnetic field, away from the magnetic field in case of an external magnet. Okay, now suppose you take a paramagnetic material. Paramagnetic material is slightly attracted towards a magnetic field. Paramagnetic material. So if you keep a material here, this material will get spread out. Why? Because it wants to go away from the magnetic field, so it will spread out. A paramagnetic material is slightly attracted to the magnetic field. A ferromagnetic material is strongly attracted. A ferromagnetic material is strongly attracted. Okay, forget about what I am doing. So ferromagnetic material is strongly attracted. I am trying to bring out the difference between diamagnetic material, paramagnetic material, ferromagnetic material. Eighth slide. Question is, what is the magnetic moment associated with the electron in the nth Bohr orbit? Definition of magnetic moment is I into area. So I into area. I is equal to Q into frequency. So Q into frequency into area. Okay. Now frequency is 1 upon time period. Time period is equal to 2 pi r by V. Time period is equal to 2 pi r by V. So if I substitute that, so I'll get Q into V by 2 pi r into pi r squared. So some cancellations will happen and I'll get magnetic moment is equal to QVR by 2. Okay. Now according to Bohr's concept, MVR is equal to NH by 2 pi. So VR will become NH by 2 pi M. So if I substitute here, it will become ENH by 4 pi M. This is the magnetic moment associated with an electron. You will learn in chemistry, this is what is called as one Bohr Magneton. One Bohr Magneton is the magnetic moment. They will teach you there, don't worry about it. But this is what is called as one Bohr Magneton. Okay, so this is the 8th slide. Yeah, then again, yeah, so I told you about these things. This is not there in your syllabus, you don't have to worry about it. I was trying to tell you there are two ways you can approach the unit of pole strength. One is from current. So this will give you the pole strength. Yeah, you get it from here itself. So you get the pole strength from here, N into I. Then again, you also mu naught is common to both. Okay. So then you also get it from this Weber per meter squared. So Tesla is Weber per meter squared. So that mu naught is common to both. Pole strength by R squared. R squared is area. Area here gets cancelled. So the Weber so Weber is another unit of pole strength. So pole strength can be expressed in terms of Weber. It can be expressed in terms of current into length. Anyway, so I was trying to explain to you the difference. Then I explained to you about domains. So what is a ferromagnetic material? In ferromagnetic material, you have too much of paramagnetism. Paramagnetism is when the individual electrons align so as to add up the magnetic fields. So there are regions where there is all the magnetic moments are aligned so that there is a strong magnetic field here. Overall it will be zero, but there are small zones where there is a magnetic field. Then I am telling you, okay, now what happens when you place this kind of a material in a magnetic field? So this is what is going to happen. A diamagnetic material wants to go away. A paramagnetic material is slightly attracted. Ferromagnetic material comes closer because it gets attracted by the magnetic field. Okay. So this is one. Next, suppose there is a magnetic field here and I keep a body, and this is a diamagnetic substance. So I said diamagnetic substance wants to go away. So this will have an influence on the magnetic field. So if you have a diamagnetic substance here, the magnetic fields tend to avoid it. So this is how the magnetic field goes around diamagnetic substances. If you have a paramagnetic substance here, that is slightly attracted. It is slightly attracted to the magnetic field. Beyond that, nothing much happens. Okay. So this is slightly attracted. So it pulls the magnetic field slightly towards itself. Now, if you have ferromagnetic material, ferromagnetic material will behave like shells, charged shells. So the electric field, the field lines will always be perpendicular to it. Yeah, and they will all go through this. So it will pull all the field lines towards it. This is a ferromagnetic material. Okay, so a ferromagnetic, this is not there in syllabus, so you don't have to worry. A ferromagnetic substance pulls all field lines to pass through itself. Okay, it provides a path for the field lines. So if there is any magnetic field and if there is a ferromagnetic material, the field lines would want to go through the ferromagnetic substance. Okay, so that's what it is, pulling the field lines towards itself. While a diamagnetic substance repels. A diamagnetic substance repels. This is a diamagnetic substance, repels. A paramagnetic substance weakly attracts, but a ferromagnetic substance strongly attracts all field lines towards itself. Okay, so this is the next difference between the three. Please make notes. Don't worry whether this is there in syllabus or not. God created lot of materials. So there is one diamagnetic material. Now if you are asking me what is the use of it, there are lots of uses of it. One, now suppose you have I have undergone an operation and in my hands I have put a stent. Now do you want that stent to be magnetic or non-magnetic? So I have a stent in my hand. I have a stent. Stent is something that is put to support the bone. Suppose some accident happened and my bone has got damaged, I can sew it up with the help of a stent. A stent gives support to the bone. Now I definitely don't want a ferromagnetic stent. Yeah, so there are lot of uses depending upon industry. So you would want it to be non-magnetic. Now, yeah, so non-magnetic means you would want it to be diamagnetic. So like that we can keep thinking about lots of uses of that. Okay, so good. So now here this is what I have. So ferromagnetic substance pulls it towards itself. So diamagnetic I explained to you. Next, if I take a diamagnetic substance, if I take a diamagnetic substance and heat it, what happens? Nothing happens. If I take a paramagnetic substance and heat it, its magnetism decreases. Why does the magnetism decrease? Because now the electrons have more energy. So when the electrons are having more energy, they are more randomly moving. When they are more randomly moving, the atomic magnets are kind of cancelling each other out more. As a result, the magnetism decreases. Okay, so when in case of a ferromagnetic material, when you heat it, now this will show significant decrease in magnetism. So when you heat a ferromagnetic material, it gets converted into a paramagnetic material. At a temperature which is called the Curie temperature. That means beyond the Curie temperature, all ferromagnetic materials are paramagnetic in nature. So up to the Curie temperature, all ferromagnetic materials become, above the Curie temperature, all ferromagnetic materials become paramagnetic in nature. Okay, so if you can make some notes, we will move on. Curie temperature is that minimum temperature, is that temperature above which a ferromagnetic material becomes paramagnetic. Okay, so I hope you have understood Curie temperature. Curie temperature is that temperature. So for paramagnets and ferromagnets, for paramagnets and ferromagnets, as temperature increases, magnetism decreases. Beyond a particular temperature called the Curie temperature, ferromagnets become paramagnetic in nature. Okay, so if this is understood, then we can just move on. So here I am having a ferromagnetic material. Okay, I'm having a ferromagnetic material. In this ferromagnetic material, there are a lot of these domains. I already explained to you. Okay, so I'm not going to waste my time drawing that. So there are a lot of domains. Now I have exposed it to an external magnetic field. Okay, I have exposed it to an external magnetic field. This is an external magnetic field. So now when I increase the strength of the external magnetic field, more and more domains get aligned. So the magnetism increases. And after some time, whatever could have aligned. So now that goes flat. So now even if I didn't increase the external magnetism, nothing happens. Yes. Now I'm bringing that external magnetism to 0. So lot of them get disoriented, but still a few are oriented in that direction. So there is some magnetism. Now I'm creating a reverse magnetism to even disturb them. So I created a reverse magnetism and it reached here. Now I'm increasing the strength of the reverse magnetism. So again the same thing happens in the opposite direction. Yeah. Now again I made it 0. So again there is some magnetism. So again I have to give a reverse magnetism to make it 0. Then again I'm increasing the magnetic field in that direction. So do you see, this is how the magnetism in the surroundings change with change in the external magnetic field. So an external magnetic field is applied to a magnet, a ferromagnet. So the magnetization has changed this way. Do you understand this? If two diamagnetic spheres are placed near the south pole, one after one, how is the second sphere which is away from the magnet directed? I have no clue. Give me time to think. I hate to teach this part of the syllabus because you don't get questions from here in the entrance exams. So it's all memory stuff and I am very poor memory. Okay, so let me finish my stuff. Okay, see, I have a ferromagnetic material. It is unmagnetized. I am having an external magnetic field which I can keep changing, and I am trying to look at the intensity of magnetization. Okay, so how much has my material got magnetized? So it started with 0, domains are aligning themselves, and after some time I've seen that all the domains are aligned. Then I changed it to 0, but now it has not become 0 because there are some domains still aligned in the direction. Then I had to bring about a reverse magnetization so that it became 0. Then I'm giving it a reverse magnetic field, and I see that this is what happens. Then again I brought this to 0, it reached here. So again I have to take it here, and then again I have to take it here. So if I take a magnet and if I put it in a varying magnetic field, a ferromagnet, and put it in a varying magnetic field where the magnetic field is going north, south, north, south, north, south. So this is how the magnetism is changing. This distance from here to here is what is called as the retentivity. That is, once the external magnetic field is removed, how much magnetism is retained? Yeah, once the external magnetic field is removed, how much magnetism is retained? That is what is called as retentivity. Now, if you want to have a permanent magnet, you would want high retentivity, so that even after you have removed the external field, the amount of magnetic field remaining is still high. So you would want a curve which looks something like this. Yeah, so the retentivity is high. Okay, now that reverse magnetic field that you are applying here to make it 0 is what is known as the coercivity. Coercivity is the reverse field that you are applying on a ferromagnet to make its magnetism 0. Now, if you have a, if you have eddy currents, right? Eddy currents. I'm sorry, not eddy currents. Some example which I have already taught to you. Okay, suppose there is a ferromagnetic material and you are going to use it in an AC application, say transformer core, okay, where the direction of current keeps changing. So if the direction of current keeps changing, you are going to be constantly magnetizing and demagnetizing. Now, you don't want it to lose energy. So ideally, you want it to be like this. That is, when you increase the external magnetic field, that is, when you're increasing the current, the magnetic intensity should increase. Decrease, decrease. And this, you don't want any coercivity and retentivity. That means you want low coercivity and low retentivity. Yeah. Now, if you are having a generator, in a generator you are using a permanent magnet. So that material should have high retentivity and low coercivity. Yeah. So this is the only question that has ever come in an entrance exam from this. That how do you relate the use of a material to its coercivity and retentivity? Okay. Permanent magnets, high retentivity. Electromagnets, ideal electromagnets, very low retentivity. This is the ideal curve for magnetization, demagnetization. This curve that you saw here is what is called as the hysteresis loop. Hysteresis loop. Hysteresis loop gives you an idea of how much energy is lost every time a ferromagnetic material is magnetized, demagnetized, and again magnetized. That means the area of this loop. So you want the area of this loop to be minimum if you are using it as a ferromagnet. And this is that situation where we are using it as a ferromagnet. Okay, so next class I will talk more about this. We can just move on. I'll just check if there are any doubts. Sir, this graph needs a previous record to take its next decision. This recorded section, okay, that is a different thing. To diamagnetic, Sriniti, I don't understand your question. Once I understand, I'll answer. This graph needs a previous record to take its next decision. Only once. After that, it follows. After that, it follows. Yeah, I will show. So when a ferromagnetic substance is placed in a find field, all domains arrange in the same direction, right? You can't say 100% because we are talking again about electronic activity. Electronic activity cannot be predicted. It can only be said that majority will be like that. It's like, you know, you school having 4,000 children and somebody saying attention. How many of you are really going to attention? Few people will be going, but not 100%. Yeah, yeah. Tomorrow we will discuss this again. Okay, please read and come. You please read and come. Tomorrow we will discuss this again. Yeah, but this is deleted portion, so you can just relax a little. Second slide, third slide, fourth slide, fifth, sixth. In the last class, we were discussing about that semicircular loop. So there was some error that we have made. There, not that error we have made. There's an alternate solution to that. So I will demonstrate that solution also tomorrow. So I'm not saying what I have done is right, nor am I able to say what I'm going to show is right, because I am not able to find the mistake in my case. So if anybody can think about it and tell me, I'll be very happy. So this is the 8th one. Tomorrow we'll discuss that. 9th, 10th, 11th, 12th, 13, 14, 15, 16, 17, 18, 'Yeah, so I'll be teaching all this tomorrow again. So tomorrow it will be regular time, Senthil. Today I was outside. It took me a little time to come back. So that's when I had to request you all to come at a little later time. Tomorrow it will be regular standard time. Okay, there won't be any change tomorrow. Okay. Yeah, okay, sure. Thank you. Thank you.